Why is there no recording? That's weird. I'm sorry. This recording has been cut. Yeah, I'm just going to reintroduce quickly what's going on here because for some reason my recording didn't work. So now we're working. Now we're fine. Yeah, back and forth. We have the new recording of lecture to advise everyone to watch it because this is very helpful not only for grading but also for the for your development as a good elaborate engineer and researcher. Research diary, nothing new here. And assignment 6, yeah, which we've just been talking about assignment 6. There's the folder inside the archive here, namely this archive. And let's have a look at the notebook. Once again, there are a couple of helper functions here, a couple of schemes that will be used in the notebook, and that's it pretty much. So let's go and see what's in the notebook. So it's based on some CS 109A course on probably deep nets. I'm not sure what this course is about. Let me see. I'm very curious. Oh, Harvard IAC. So there's this course, Introduction to Data Science, and they have pretty much the same like structure as ours, but this is like these assignments are taken from their repository and kind of like adjusted. So here, just import usual stuff, and there's let's just break down once again what we did on lecture, but in a practical manner, what the neural networks look like. Well, obviously, simple way is just we have an input x and output y. We have an auxiliary variables, they call it z, which is basically just weights applied to our input, and the bias term b added. Weights are w. Then we have this auxiliary variable processed by an activation function. In our case, it's a sigma z or sigmoid activation function. Yeah, for the reference, sigmoid is just I'll show it again because there was not a recording. It's just something like this. It looks like this in Python. In the numerator we have 1, in the denominator we have 1 plus the e to the power of negative z. Pretty much that. Negative z, these is our input z, obviously. So yeah, let's go on. There's each time step of the model of the network is depicted here. So we just have this main part, which is called like hidden part or hidden layers. And x and y is just considered, this is the input vector, right? It could be a vector, like something. And y is also like output, could be a class or scalar or something. And inputs are linearly combined according to some weights and bias. So this is called an affine transformation, nothing too unusual here. Basically, Perceptron allows the weight input transformation according to the activation function, and single perceptron is just they have only one output, obviously, and in the end there's also what's this? Single error of the network. I don't know. Well, obviously they kind of reoccur at each kind of epoch or step. So we'll refer to these as steps right now. So this can be processed multiple times to optimize the cost function or the loss function. And basically, let's have a look what basically such a single neural setup gives us. Neural network setup. So we have to kind of like predefine weights and biases somehow, and we also need to choose activation function. And for now, yeah, we will manually specify them. Have a sigmoid activation function, which is a great thing here. Something that I just showed, this one, and also we have some questions on the limits of sigmoids, and obviously. Starting to infinity this from 1 to 0. the range of the value of the function is like from 0 to 1, asymptotic, and this is just a logistic family of functions, and sigmoid is just a bright representative of them. Once again, as I mentioned on the lecture. Yeah, so we have to plot the sigmoid here. Obviously, you can load the sigmoid pi file here. Something that is in here. It's kind of like not this for you to work through. Sigmoid pi. This basically the script, or just copy paste. This is much better, faster, and more efficient. And plot the sigmoid. Can show some things from my notebook. Maybe, yeah. So just observations. Yeah, let's just go on. And then we have to generate 500 points for NP-link space, or like for 10H you can basically use either sigmoid or hyperbolic tangent, but you have to like generate an linear space with numpy from range like with -5 to 5 with equal uniform distribution, 500 points. That's it. Just calculate them, plot them. You just plot them first, and then you kind of realize that there's a concept of activation in neural networks. So either the condition is satisfied, and otherwise, and then the gradients, the calculation flows further. If the condition is not met, well, it doesn't. And obviously here they see that x is like this with this negative bias coefficient over weights. This is a representation, and sigma, that's like observation according to this distribution, I guess. The sigma should be 1 over 2, and the steepness, or like the coefficient, is going to be defined by w. Lots of under the hood math, kind of, in a way, but it would take some time just to get used to it and to start to understand things better. And then you actually have to approximate a Gaussian function using a node. Yeah, for demonstration purposes, the Gaussian distribution, or just Gaussian function, is going to be this. So, e to the power of negative x squared. It's nothing too unusual here. And then we have this real function, we have link space input. We just plot it all. We have access. Let me see if I can do this. Generate things. Sigmoid. Because this probably there's nothing too unusual that I cannot show. Let's do this. Okay. Run this. Run this. Yeah, so you have this nice little perfect Gaussian distribution with mean 0 and standard deviation of 1, I think. Yeah. Then we apply a find function, just wx plus b. So it should be w times x plus b. Let me do this in a fancy way. Okay. So we can, of course, load a find, but that doesn't quite require us. The sigmoid also here. So we set up manually. I don't know how do they choose these parameters ad hoc, but okay, let's just see. We specify the weights, the weight to negative 4.5, and b our bias to like 4.0. It's important that these are floating points, not integers. And then we just apply the affine transformation, just do this thing, multiply x by w and then plus b, and then we apply sigmoid to it. I don't know what h is supposed to mean with a semicolon, but fine. Oh my god. Yeah, there's something happened here, that's good, it works. And then we have next thing, basically weights are readjusted, bias also readjusted, and we perform a find, but now we kind of like decompose this. We do not do this in a very stupid, pardon my French, a very inaccurate way to portray a nested functions in Python. It's better to be iterative. First define z with a fine transformation, and then define h, which is going to be sigmoid of z. So let's do this. Now plot the activation function and the true function. So we have a good approximation on the right, but not quite a good one on the left, with a single neuron though. And single neuron obviously returns the output at this point, at this breaking point. Either has it or doesn't have it. At x equals 0, so somewhere, yeah, they even say here. So if the neuron is on until about 0, and then it starts to die out. Basically, this kind of like a threshold potential of each biological function. Neurons, like biological neurons, any other neurons. Artificial ones, I mean. So it's able to get close to the true function, but not even close to like the common approximation of the true function. So we can change weights and biases even more, and changing them will impact this plot, but we do not know if we can approximate the function. Obviously, this is a Gaussian distribution with a single neuron. Can we? Yeah. There's an observation as well, so we have like sigmoid from the affine transformation. It looks like a composition of functions, that's true. And that's what neural net's doing, just stacking things, stacking functions. Building approximations by stacking these functions on top of one another. Composing like 3 functions would be written like this, basically, nothing too bad. Now, of course, let's experiment more with weights and biases. We have this list of weights, minus 5, 0, 1, 5, 0, minus 1, 1 for biases. Now the plot, true function, labels. Let's see this. So we'll have some other very kind of ugly and awkward scenario here where the high weight value, like the opposite of -5 and like slightly bigger bias, higher bias, just results in the completely opposite thing to the orange initial line. The green one with a very small weights just does a linear function, and obviously not even close. This is the worst line, the negative bias. And we obviously didn't do the exhaustive search of W's and B's, but Perceptron probably does not have any capacity to match the actual function. Obviously, something that I mentioned before. And this is not surprising at all. This is because the output of the network is just a logistic function. And we can only like tune the weights and biases and try to understand if this works, but this will never work. So what we can do is just try to diversify the model, try to add additional nodes, additional neurons, additional layers, kind of, right? Not layers, but nodes. So yeah, single neuron is quite limited in its potential accomplishments. We want to expand the number of nodes. And how to do that? We just add an additional kind of like layer here, like not layer, but a section here that just traverses below as well, like below the original input and hidden layer. And we can also like stack them on top of each other, put them next to each other, so one to another, so like a layer-wise or width-wise or depth-wise. Doesn't quite matter, but in the end it does matter, like when it comes to serious networks. The following figure, yeah, obviously we have this Z1, Z2 with affines, transformations. Then we have H1, H2 with activation functions applied. Then we have this Y, which is kind of combines these two into and just multiplies it with the output weight and output bias. And this is a single input in this case, no like multiple x's, just one x. And this is not like the case in deep learning or neural networks. Usually there is much more to the x or to the input itself and just singular x, but still. We'll just keep things simple. And each node has a weight and bias associated with it. That's kind of self-explainable. We can perform affines here from now on to get these. And then we have H1 sigmas, and then the nodes are combined to give the overall output. We have the node that is on top, and the node that is on bottom, the H1 and H2. There are multiple ways of doing this, obviously, and here they just take a linear combination of the node outputs to produce the actual prediction. And there are like separate weights for this, and it's kind of nothing too fancy. Let's just see how this works. Yeah, we just have to compute the separate outputs for each neuron. So generate data. We just approximate Gaussian function. Input the weights and biases. So basically, for both oh my god, both sections, or both layers and nodes, for each node we use the same value but with different signs for weights, and we use the same bias. So we take the first element of that list and add like the first element of that list, we get Z1 and Z2 respectively, and then we just apply sigmoid. Here actually this is weird, we have a sigmoid function, but for some reason they decided to use H1, H2 and just write it from scratch. Anyway, I'm fine with that. Let's plot the thing and have a look what's going on. Something much better, probably. Yeah. So they kind of do not by themselves, the neurons by themselves are not approximate, but in general, this looks something very similar to the truth. And the network prediction has to actually make use of both sigmoid curves, and we have to add, for that we need to add H1 and H2, and without any weights, and just have a look. We're not doing classification here. What? Predict an actual function, sigmoid activation is convenient. Yeah, okay, so let's just go. And here we set the output weights once. This shouldn't be unity, this should be ones. And we just set bias to 0, no bias. And then we see, so constant weights, nothing changes. And have a look. Plot the same thing and see. The true function is slightly lower. And we need to adjust. We need to adjust, even though the distribution kind of like matches the original one perfectly, we still need to adjust the y-axis. We just need to lower it down to the blue dashed line. Even though like our outputs H1 and H2 summed up, they do a good job of like having very similar to what we're looking for. It's still not good, but it's pretty sophisticated. We have just 2 neurons, but we get some pretty interesting behavior. So it didn't do anything, and let's see if changing the weights on the output does something. So here we have weights in the output negative 1.5 and negative 1.5 for both cases, and bias 1.5. Why 1.5? Because we want to kind of like skew this towards across y-axis down. So the middle point of this whole distribution at the top orange line lies within 1.5. So they decided, okay, let's do 1.5. Yeah, let's see. And oops, something wrong happened. It kind of like mirrored it down. Probably something with bias, or maybe probably weights as well. But what happened here? So briefly, it just kind of matched the distribution, and then it mirrored. It did basically a vertical flip, not a horizontal, but a vertical flip. So basically, almost there, but not quite. So they kind of doesn't match the true function, but we're moving there. We're having some hopes, and looks quite like Gaussian. Yeah, did look like Gaussian even here, but let's not take that into account. So we can change the number of nodes, we can change the activation functions, change the weights. Yeah, many experiments here. This was all that like initial data science, not data science, like researchers did. Like they played around with this, with these activations and nodes and calculations and etc., and then kind of approximated many different functions. You have read through this. Well, I'll explain some of the things. Obviously, this is our additional kind of like notion of the affine transformation. This is a adjusted transformation, yeah, of the, and the usual laws, factors, conditions apply, and then just apply sigma in here. It's been a while since I read through this. Yeah, that is a finalized mathematical notation of this. So kind of like this was just for you to understand how a single neuron might not be always enough. Maybe 2 neurons are enough, but not quite. Maybe just also stress the importance of weights and biases in the output layer, like so that you don't get something like this. Well, this is kind of funny. And yeah, all the necessary information is here for you. Let's talk about your home task. We're coming to it. So here you basically have a simulation of a typical, I would say, deep learning interview. You are like, you come to an office, suppose there's no like, you have an opportunity to come to an office and you, like, an interviewer prompts you, like, writes this image, like, paints it down, sketches it down like this: input X, output Y out. And it has like one hidden layer, right, but with 2 nodes, and asks you to perform backpropagation. And backpropagation is something we talked through on the lecture. I'll quickly show it here. Where is this? So this thing, with partial derivatives, with chain rule, how to calculate this and stuff. You can watch, you can have a look in the lecture. We'll try to explain now as well, but let's focus on the home task first. So here we have a one hidden layer neural network, which has 2 neurons, so 2 nodes. Once again, 1 neuron, and second. This is called hidden layer. It has an input X and it has output Y, like this. So basically, it has the output and the activation function is not sigmoid here in the end, but just a linear one. And linear is depicted as ID of Z3. So you just don't do anything with this. You have to calculate Z3, backprop through it. And just for more explanation, we have X, right? And the X traverses here and here to the bottom and to the top node. Let's have a look at this node. Here, basically, we do have Z1 first. So we have relevant and appropriate weights and biases for this term, namely W11 and B11. You just perform affine transformation first. Then you perform apply activation function. This is sigmoid, this is like sigma of Z1, and you get H1. Same is done here, but for the lower node with Z2 and with weights W12 and B12. Once you get this, there are H1 and H2. You couple it up in the output. You first calculate these 3, which is going to be the weights to1 times Z1, so this one, a new set of weights. Once again, just to make things clear, that you're kind of like not lost and confused. Let me do this in Paint. Wait. So this has W11, and respective B11. This has W12, sorry, and B12. So it's kind of predefined on this edge, right? No, kind of like if we interpret this plot as a graph, this is an edge, this thing. So this lies within the edges. And these other things, and these other things, I don't know, maybe might have been better to use a different color for it, but you understand the idea. And also this is the thing, and this is also the variable, or our like scalar. In here, same thing applies. W21. Yeah, bias. It's a good question here. I'm not going to spoil too much fun for you, but as far as I remember, I did find a mistake in this task, in this picture. So maybe it's kind of like a tip for you. Maybe something's wrong. And the way to is here. So these things, they kind of like capitalize from these final edges. It's just different color. They capitalize from these edges, and they participate in calculating the final Z3. So this you kind of take. This already exists. So does this, maybe. And Z1 and Z2, you kind of already received here. These things, Z1, Z2. And finally, once you calculate Z3, you can just do nothing with it, with identity function, and get a Z3 output of the network. And this is kind of like how the flow goes. For better understanding and for better understanding and for the kind of like not being lost in all these variables, where they come from, etc., etc. So you have this task. You need to perform backpropagation for this network. Yeah, for that, you basically have all these functions you need, which is affine, which is sigmoid. You probably don't need Gaussian, sigmoid derivative. Yeah, you will need to calculate derivatives, of course, which is just the derivatives with respect to, I don't know, z1 over these, like derivative, it's a Greek t, over the like theta 1 or something like that. It's kind of like you'll get the hang of it later. Mean square error, I don't know what that's for. Probably for some other tasks. So what is this? You are given the array initialization. The input is x equals to 1.0. You have weights and biases 1 and 2, right? And then you have supposed to first do the forward pass to calculate these three, and this is going to be out. The first output in this picture is going to be a forward pass. So you first flow like this. Let me see. So you first flow like this. Hopefully this is called forward pass. The first ingredient in training neural networks, and then comes backpropagation. But before backpropagation, you need this kind of like output. This is the result. Before backpropagation, you need to do a forward pass, so this thing, like this direction, across here. But then backward pass is kind of like self-explanatory from the name. You have to propagate back, like, let's see, this is the whole direction of backprop, right? And this goes like by calculating partial derivatives here. The z3, dj theta. Theta is like weights. I mean, have a look at the lecture. You just have to go node by node, like this, here, and this is kind of the vector, the reverse update. And then you end up in the initial like starting point in X. This is backprop. First to do a forward pass, calculate Z3. Then you apply Gaussian. Oh yeah, that's why I need Gaussian, I see. So the Gaussian is applied, and you kind of need to try to model the Gaussian distribution. And the question asked here is whether the output, your output that you calculated, match the actual value of the function of the Gaussian. And then you have to calculate the derivatives here, make a loop to update your weights, right? So backpropagation, we go forth and back. And then you do again the forward pass. And you have a look at the output. And you compare whether the output has become better looking to the actual distribution here, the Gaussian one, than before. And then you have to combine this into a loop. For 50,000 steps, so each run through is a step. The learning rate is the eta parameter, which realizes how quickly you want to converge, how large of a step you want to make towards achieving your potentially global optimum. The same thing is initialized here. This is the same input data as here. And you just have this kind of like a template for a loop, where everything is kind of like described for you. You just need to code it down. Random choice, you have a random x, right? From this linear space, just get random input, right? And then you forward pass, you derive your partial derivatives, and then you update weights. So this is backpropagation, this part. This is forward propagation, this is backpropagation, lines 18 to 22. And then you have to like plot this and have a look, I guess. And also there's a classification task, maybe. Yeah, this is also pretty much the same. You just generate data from Panda support data frame. This is pretty cool. Weird style, but still. So we have this kind of data set of randomly generated points with make blobs, 2 classes, and you do the same thing. You split, everything is split for you. You just use the test for some reason. Maybe that's wrong. Maybe you should have train. I don't know. So W1 and B1 is given for you, just constants ones. And then you have like Z1 calculation that you have a dot product here. If I'm not mistaken, this is the same as writing this. Let me see. Like that. But this is also the same dot product, but it's just the Python built-in function. Just a tip for you. Yeah, and then you apply the sigmoid activation function to Z1, get H1. Sum the predictions. Just calculate the metric, very basic accuracy. Have the accuracy 0.45. Then you loop it. You also want may want to set up a batch size, just to take a couple of instances at the same time to kind of make the network converge faster. Like initially, once again, I'm going to demonstrate this. There are 2 key core concepts. I'll do this in a separate cell. There is learning rate and batch size. So learning rate or eta and batch size just BS. Don't confuse it with something different. So batch size, the higher the LR. I'll just make sure this is this. The higher the LR, the more opportunity you have to increase BS, batch size. So batch size, basically the higher the batch size, the slower the model converges step by step. So it just doesn't overfit on the data, doesn't extract too much information at each time step. And if you have a large batch size, like say 128, then you can afford yourself to put a higher learning rate. if that's like in the capacity of your machine. And of course, this works vice versa. The lower the learning rate, the more the bigger batch size you should make. These are just practical tips from me. So if you have low learning rate, I have a nice this picture from the lecture suits well. So if low learning rate is applied, so this ball, this weight updates, ball kind of does very small steps, like it doesn't rush anywhere to find the global optimum. So if you decrease your batch size, make it small, make it 1, anything, this makes it faster and more like resistant, and overcomes the problem. But if you have like a high learning rate, it's probably be painted in the paint. Let me see. So we have this the same situation here. There's our initial starting point, going to be marked by red. So this is the global optimum. This is our target, kind of like a flag here. Yeah. So we try to get here. And step by step, we have an optimal. If we have an adequate learning rate, we should go like this, along the valley, and we start to slow down here and go here. This is decent, I guess. There are some different strategies, different optimization techniques and stuff. And if your learning rate is too low and batch size too low, too high, I mean, if that kind of like diverge, then you slowly do go along fairly. And you probably might not even converge, but you do. These are all steps for your. Let me just draw it in a better way. Like you slowly. This takes forever. It might even converge. And if you have too high of a learning rate, like a blue one, you have like this, the initial point, right? And you have this step, and then this step, and you kind of almost there, right? You're almost here, but not quite. But the next step just goes here, boom, and boom, and then you kind of diverge, and this is the worst case. So you have to be careful. So batch size has to be directly proportional to your learning rate. So if your batch size is plus like a big batch size, then your learning rate is also has to be plus, kind of like from practical experience. If you reduce batch size, if you just put a neutral like plus minus batch size, if you reduce it, then you probably need to adjust the learning rate accordingly. So you need to yeah, if you like reduce batch size from 2 pluses to plus minus, it converges faster, but you need to make learning rate like a minus. A good minus, so you need to reduce this, if you increase this, and these are kind of like it has always been like that, and you kind of have to memorize it and keep track of it because this is quite important. That's the desktop. Any questions pertaining to this part I've explained so far? Sorry for not giving you any opportunity to speak. Any questions? Maybe something's unclear, or you have like comments or something?
Clear.
Okay. So yeah, this I showed you, but you just choose batch size here, same skin for you, and you kind of like copy paste your loop from this part. Sorry, this doesn't work well. You have the code here already. You just reinsert it here and make sure it runs and check your accuracy on the test set. That's it. Well, that's pretty much it from the home assignment. Once again, take your time. There's no need to rush or like to worry about the deadlines. I know the situation is quite rough right now in Kiev, so or wherever else you are. So no worries. There are no further questions. I shall wish you a safe and a pleasant end of the week, and See you guys on Friday.
See you.
Goodbye.
Yes,
Thank
bye.
you for the practice.